Hello, Professor. Today we're gonna discuss about PCA, the simplifying complex data. And we take this topic from eigenvalue and eigenvector. My name is Lauryn, and my student ID is DSC2409079.
Hello everyone, my name is Avril from Muljono and my student ID is DSC2409079.
Hello everyone, my name is Avril. My student ID is DSC2409076.
The first one is Introduction to PCA or Principal Component Analysis. The definition of PCA itself is a method that turns a data table into a smaller set of variables called Principal Components or PCs. The purpose of PCA is to simplify data and create structure in multivariate data by reducing the dimension. It is also known as identifying the linear combinations of variables that account for the most variables in the data. Functions of PCA are actually a lot, including preprocessing, which is before feeding data into machine learning models. PCA helps clean and simplify it. It also used in pattern recognition for identifying trends in data, such as clusters in customers' behavior. Signal processing, analyzing signal like sound or images for trends. Predictive models, simplifying input variables for faster and more accurate predictions. The next one is the role of eigenvalues and eigenvectors in PCA. Eigenvalue is useful to measure the size of variance that captured by a principal component. Meanwhile, eigenvectors are used to determine the direction of each principal's component, while eigenvalues tells us how much. Eigenvectors tells us where. For example, in an image dataset, eigenvectors might represent specific features like edges or colors, while eigenvalues tell us their importance. The next one is step-by-step in PCA. The first one is standardize the data, or standardize the range of continuous variables in a dataset. This involves subtracting the mean and dividing by the standard deviation for each variable. Standardization ensures that all variables contribute equally regardless of their original scales. The second step is compute the covariance matrix. Once the data is standardized, we calculate the covariance matrix, and this matrix captures how the variables are correlated with each other. High covariance values between variables indicate strong relationships, which are crucial for identifying patterns. The third step is finding the eigenvalues and eigenvectors. The covariance matrix is then decomposed into eigenvalues and eigenvectors. Eigenvalues represent the magnitude of variance captured by each principal component, while eigenvectors define the direction of these components in the feature space. The fourth one is create the feature vector. Next, we form the feature vector by selecting the eigenvectors corresponding to the largest eigenvalues. This step determines which principal components will be retained based on their contribution to the total variance. And lastly, the last step is the fifth step is recast the data. Finally, the data is projected onto the new axis defined by the selected principal components, and this recasting simplifies the dataset, making it easier to visualize and analyze while retaining most of the essential information. This structured process helps transform complex datasets into simpler forms, enabling more efficient analysis and visualization while reducing the redundancy. The fourth one is application of PCA. PCA is highly versatile and has many practical uses in a lot of fields. For example, image compression. Imagine you have a high-resolution photo with millions of pixels. PCA can help reduce the data size by focusing on patterns like shapes or edges rather than individual pixels. This makes storage and processing progress faster while keeping the image recognizable. And from the picture below, the left side is the original space from 3D to 2D, and the graph has three axes, x1, x2, and x3, representing a 3D space where the data points are spread. The black axes represent the data in this 3D space. The goal of PCA is to simplify the data without losing a significant information. Now is the principal components or PCs. The red line or PC1 is the first principal component representing the direction of maximum variance in the data. This is the line along which the data is most spread out. The blue line or PC2 is the second principal component, orthogonal or perpendicular to PC1. It captures the second most variance in the data. Together, PC1 and PC2 form a plane that retains the majority of the information in the data while reducing its dimensionality. Meanwhile, the right side is the reduced space or the 2D one, and the new axes are now PC1 and PC2, which are derived from the original data, and the original axes x1, x2, and x3 are no longer used. The data points are now projected onto this 2D space defined by PC1 and PC2.
To apply this PCA method, we can apply this for this scenario given. A city government is analyzing the performance of public park based on two features. The first one is number of daily visitors, and the second one is the amount of maintenance costs. So there's given data X, where the first column represents the number of daily visitors, and the second column represents the amount of maintenance costs in $1,000. So, as my friend has explained the step to find PCA, the first step is we need to find the mean of each column. So we need to find the mean for the first column. To find the mean, we just need to add all the data and divide by the amount of the data. So from the first column, we have data that represent the number of daily visitors. So like the first day is 8 visitors, while the second day is 2, 5, and 9. So just need to add all of them and divide by 4, and we get 6. And this also applied if you want to find the mean of x2. So to find the mean of x2, just do the same. Need to add all the data and divide by 4, and we get 4.5. And the next step is we need to find the x center. To find the x center, we just need to subtract x and mean factor. The mean factor is from what we get just now, is the mean, and we change it to factor form. And after you subtract, then you get the x center. The next step is we need to find the covariance matrix. So to find the covariance matrix, there's formula given the PPT that covariance is equals to 1 over the amount of data subtract by 1, and do a dot product between x transpose center and the x center its own. So the first step is we do a dot product between the transpose of x center and x center. So first, that is the x transpose center, and we just need to do the dot product, and we get that. The first column is 30 and 23.5, and the second column is 23.5 and 90.25. So after that, we just need to times with 1 over n minus 1. So n minus 1, n is 4 because we have 4 data. 4 minus 1 is 3, 1 over 3, and divide with the matrix that we get before. And we get the first column is 10 and 7.833, and the second column is 7.833, 6.417. And the next step is to find the eigenvector and eigenvalue. To find the eigenvalue, for what we learned during the class, that you just need to subtract the matrix with identity times eigenvalue lambda, and need to find the determinant of that. After that, we will get the quadratic equation. Then from the quadratic equation, we can get the lambda 1 and lambda 2. That is the eigenvalue. And for what we get, the lambda 1 is 15 and the lambda 2 is 1. This is not exact because the exact number is for lambda 1 is 15.8, but we round it up become 15, and that will not really impact too much to our
PCA data later. Next is we need to find the eigenfactor. So for the eigenvalue equals to 15, we get the phi1, the eigenfactor equals to 0.8 and 0.6. For the eigenvalue equals to 1, to find this, we just need to compare this all to our computer to solve it for us, and we will get phi2 equals to minus 0.6 and 0.8. And after that, we need to check which eigenfactor that we want to use, which eigenfactor that will retain the most data from the original data set. So to check that, we need to total the variance. So we need to add the lambda 1 and lambda 2, so we get 16. Let's try the first component. The first component, lambda 1 is 15 divided by 16 times 100. So this we get 93.75%. From this 93.75%, we know that if we use first principal component to reduce the data set from two-dimensional to one-dimensional, you still retain 93.75% of the information from the original data set. So we will use the first principal component, that is phi1 equals to 0.8 and 0.6. So to find the PCA, we just need the dot product between X center and phi1, the eigenfactor. After we done the dot product, we will get the PCA, the data with PCA method. So we get 2.7, minus 5, minus 1.1, and 4.3. So what we can conclude from the PCA data that we get from the counting is, as we know, the first and the fourth row, they are positive, and a positive PCA score means that the data align well with the principal component, which is the direction of maximum variance in the data. In this case, the principal component is a combination of visitor and maintenance costs. This suggests that the first and the fourth row reflect the part where the visitor and the maintenance costs scale proportionally. But the second and the third row, they have negative value, and this negative value tells that this point deviates in the opposite direction of the principal component. A large negative score like minus 5 in the data indicate imbalance, such as high maintenance cost but relative fewer visitor, or high visitor but very low maintenance costs, that possibly leading to a poor quality or overuse. So to conclude this all, row 1 and row 4 reflect par with a good balance between visitor number and maintenance costs. They align with the main trend in the datasets, where this factor vary proportionally. For point 2, with a large negative score, may indicate an outer part that inefficient or unusual in its visitor to cost ratio. Point 3, with a smaller negative score, suggests that it's slightly inefficiency or deviation from the expected trend, but it's not so extreme.
Now let's use a simple example to understand how PCA works. Imagine a dataset with only two features like height and weight. We can plot this dataset as point in 2D plane, where height is on one axis and weight is on the other axis. However, if we want to analyze variation in the data, PCA transforms this dataset into a new coordinate system. In this new system, each point is given a new set of x and y values. These new axes don't correspond directly to height or weight anymore. Instead, they are a combination of height and weight, called principal component, The first principal component, or PC1, is chosen to capture the most variation in the data, and the second component, PC2, captures the remaining of variation. Now, PCA is particularly useful when we want to reduce the dimension of the data. For example, if we decide to keep only one dimension, it makes sense to retain the principal component with the most variation, PC1, by dropping PC2, which contribute the least to the dataset's variation, that we lose very little information while simplifying the data significantly. PCA become even more valuable when working with data in 3 or more dimensions. Let's consider a 3D dataset, which we can visualize as cloud of points in space. It is difficult to analyze patterns in this form, so PCA helps simplify the data. Imagine looking at this 3D from different angles, just like finding the best camera angle to view the entire scene. PCA rotates the axis of the data to find the best view, ensuring that the new axis, called principal component, captures the most important information. The first principal component, PC1, is aligned with the direction that captures the most variation in the data. The second principal component, PC2, captures the next highest variation, and the third component, PC3, contains the least variation. To reduce dimension, we project the data onto just the first two components, PC1 and PC2, and drop PC3. This allows us to represent the 3D data in 2D while retaining most of the variation and losing only the least important information. This transformation simplifies the dataset, making it much easier to visualize and analyze without losing key insight. Now we go to application of PCA in real life. First is image compression. For example, in digital photography, PCA can compress an image by keeping only the principal component that captures the most visual information, while discarding the rest. This reduces file size without significantly affecting image quality, which is particularly useful for applications like online photo storage and transmission. Second, finance. In the financial sector, PCA helps identify key factors that influence stock market fluctuation. For instance, by analyzing hundreds of stock prices, PCA can reduce the dataset to a few principal components representing major trends like overall market movement or sector-specific behavior. This simplifies complex financial data and helps analysts make better decisions. Lastly is biology. PCA is extensively used in biology, especially for analyzing gene expression data. It helps identify dominant patterns by reducing thousands of genes and expression variables into a smaller set of principal components. This makes it easier to understand which genes are most relevant to certain disease or biological process, accelerating research and diagnosis. Now we can talk about the advantages of PCA. First, PCA could be help us to reducing a big data to more smaller dimension. Second, PCA removes multicollinearity, so it makes us to read our data more easy to understand. Third is PCA could help us remove irrelevant noise in data. Next, PCA also help us reduce model parameter in machine learning. And lastly, PCA reduce model training time. Next, we also talk about the PCA limitation. First, PCA contain high computational cost, loss of interpretability, loss of information, linear assumption, and lastly is sensitivity to outliers. In summary, PCA is a powerful tool for simplifying and understanding complex datasets. It is not only reduces data dimension, but also helps us grasp key concepts like eigenvalues and eigenvector. Mastering this concept through PCA can greatly enhance our skill and provide a strong foundation for future career growth in data science and machine learning analytics.
Thank you for listening to our presentation, and we apologize for any mistake that we made during our presentation. Thank you.